All right, we should be here.
Hello.
Hey, Robert, how you doing?
Good, good. Well, I'm so glad to have this. This is the first podcast for me. I don't know about you, but um, it's always nice to have someone that's like-minded. And I had so many people suggest to reach out to you. I think like you and probably the I don't know you if you know Street Tips. Like you two were like the equal amount of people recommending, which is quite surprising because you don't have much of a connection to mining or refining. But I
Yeah,
mean, I
I
guess
have
it worked
nothing
out.
for nothing for mining and refining, but amateur chemistry stuff, and especially taking things that are really only accessible at lab scale or industry, and seeing a new way that such things can be made with common items is really my thing. So it really fits right in with what I do, and I loved seeing your projects. Um, Hey, I think that I would like to post this on my secondary channel if you don't mind. So,
Yeah.
I mean, hey, everyone watching, this is Robert from the channel. I'm sorry, your technology is called Semtech. Your channel is called what?
Channel is called ROWOW, ROWOW. But yeah, the technology, there's a couple of different technologies that we're developing. I'm even thinking of transitioning away from Semtech because it salts electromining, and we kind of want to stop being associated with mining. But
Okay.
I don't know. It's in the middle of progress.
Okay, good deal. Say the channel name again one more time.
ROWOW. You can find it on YouTube. We also have a website, rowow.net. So
Okay.
rowow.net.
Wow is the YouTube channel and the website. Well, hey, I have experimented with making your membranes already.
That looks like it.
Um, yeah, so this is I was going to see if this worked maybe today. This is a membrane that I made fiberglass reinforced.
Mhm.
And for those watching, Robert here has come up with a way to make not electron,
Ion.
ion permeable membranes, correct?
Correct,
So
correct.
this is for electrolysis projects that require separating the anode and the cathode so that you get the chemistry that occurs at each site divided, and you can use that to do really cool stuff. I mean, can you explain a little bit about what you've done?
Yeah, so I mean, the ion exchange membranes, to go a little bit further into them, there's a lot of different applications they have. You can select which specific ions you can actually transfer through. So, for example, iron or whatever, and that allows you to control reaction stuff. But our specific case that we started using this, originally, I actually developed this for redox flow batteries. There's I don't know if you're familiar with redox flow batteries, but pretty much, well, he is, but for the viewers, pretty much it's
Sure.
just two electrodes, a membrane, and a pump pumping the liquids between the electrode and the membrane. Really simple, and pretty much it creates a chemical potential differential, almost like an entropy differential between the two, and that charges the battery, and then you can actually continue pumping through and actually create voltage. So it's a very dirt cheap way to store energy. It's been known about for years, and the biggest limitation has always been the membranes. And the first thing I started, I'm like, okay, where do I buy these membranes? And back then you really couldn't. And even now, like they're incredibly expensive, and there's plenty of recipes online, plenty of tutorials online, plenty of instructions online on how people try to DIY them, but they're very limited. They're not really chemical resistance, or they're low in ion trans, so they're very resistive. There's just so many problems with them. But anyways, long story short, I kind of started using them for mining, and actually you develop this process where I can actually extract all the critical minerals, extract all the heavy metals. What I like to describe is salt electromining, because we use salt water and electricity to produce hydrochloric acid and sodium chlorates, which are very strong, powerful oxidizers, which can dissolve rhodium, gold, platinum, etc. All the heavy metals, pretty much 63 out of 60 critical minerals in a single step, extract it all into a concentrate powder and clean out the ore into an end product that's actually safer than agricultural soil. We have tons of anecdotal examples where we just let this sit in a bucket, rainwater comes in, and algae and mosquitoes start thriving. It's quite fascinating, but it's all based off science. There's real science of this. The memories have been the last thing that have been holding it all back.
Yeah, it's super cool. And I made one of these membranes. I'll grab so just to kind of talk about why I'm interested in this project. So Robert has come up with a way to make these membranes that are permeable to ions, but not permeable to larger molecules and things. And the way that he's come up with is to use ion exchange resin, which is available in water softeners. You grind this into a superfine powder, mix it with PVC cement, and then spray it, paint it onto stuff, and that forms your ion permeable membrane. So I haven't actually tested mine yet. I'm not sure if I've made it correctly because I had some problems grinding my resin fine enough, but I intend to test this little cell here as a flow battery, which will be similar to, you were showing me one of your first experiments that you had done with these membranes, making batteries with like iron chloride or something like that.
Yeah, that was one years ago where I built a little cell with these little cups, and I just hot glued the membranes in and put them in series, and I was able to get 4+ volts, and I actually connected it to an 18650 capacity tester and measured out at over 1 amp hour, which is pretty good for small cups, and they're not even flowing; they're just stationary.
Right. Yeah, that's what I intended to try with this. And so the process of making the batteries that you made, I believe what they do is they plate off iron on the
Yes.
cathode.
The negative side, yes.
So on the negative side, they'll take the iron chloride that's in solution, plate off solid metallic iron. What happens on the other side?
The other side, it forms a higher chlorine, or I don't want to say oxidization because obviously it's not oxygen, but it forms a higher chlorine state that pretty much has a higher voltage potential. So if that makes sense, so pretty much the chlorine actually goes over and reacts with the iron to form a higher chloride state.
Right, and so without the membrane, the two sides of the solution would be mixing with each other and just immediately neutralizing themselves, right? And then you'd get just electrolysis of some kind. You'd get chlorine gas, and the iron would be dissolved by the acidic conditions on the other side, right? So you
can use what's called a semi-permeable membrane, but the problem with a flow battery, and that's the problem with the flow battery, is when you use a semi-permeable membrane and you're trying to pump water, any sort of pressure differential between one or the other will actually push it through.
Okay,
right?
so but even so, you still need a membrane of some kind, and this is better than the semi-permeable. What I like about that was the first experiment that you showed me with those batteries is that you're demonstrating not only how this can be used for a battery technology where you're plating off iron, which is then reserved to be redissolved to generate electricity, but that's also demonstrating the mining principle because you're taking these soluble metal ions and you're plating off metallic iron just by putting in electricity. So that shows you how you can take your soluble metal compounds and refine them with this process. And at the same time, if you wanted to use it as a battery, you could. So that was a really cool demonstration. And that's kind of what I'm working on here. Yeah, so you've been using this for mining technology. Yeah. Okay. What do we got there?
This is actually, so the key difference between how my membranes work versus other traditional membranes. So fundamentally, there's this thing called functionalization. Okay, functionalization is when you actually activate the polymer group. So with ion exchange resin, I forgot the two polymers that it typically activates. But point is, traditionally, it's always done with post-functionalization. How this works is they create, in the bottom half is like a traditional method, and they'll create a polymers film, sheets, and post-functionalize it to create these channels to actually go through. And these channels have a specific ionic voltage potential, and it only allows certain ions to pass through, right? If you kind of think of it like a magnet where you only have, positive all around, right? And that only allows negative, negative to go through, right? Versus if you had negative ions all around, it only allows positives to go through, and it rejects the similar ones. What I developed instead is what's called a pre-functionalized membrane. And there is some research into this, but they're actually very, very recent, in only the last couple of years, and they use expensive chemicals, expensive ingredients. But what I realized, and with some help with some chemists online, is hey, we could just use pre-functionalized resin, ion exchange resin that use water softener, which already have that voltage potential around them. Mix it in with a PVC, you can almost think of it like a structure to keep it all together. And again, this intuitively sounds contradicting. It sounds like it shouldn't work because, right, you're completely surrounding this by PVC, right? There should be no way ion passes through. But there's actually a research paper that describes this and shows it. And the ions are actually able to jump from one to the other on over the surface layer and through the PVC in order to transfer through. And that's how it's able to have the ion specific resistance. And a lot, I hope this is too advanced, but the point is transitioning from a post-functionalization to a pre-functionalization is a key thing that makes this work and why it's so critical and like game changing. Because everyone always tries to make these membranes using expensive chemicals, does a 5-10 step procedure to post-activate them, super problematic, versus just use commercially pre-functionalized resin, mix it together, and boom, you're done.
Yeah. Okay. So to like kind of simplify what you just said. So basically the commercial way of making these ion exchange membranes, and one of the reasons why they're so expensive is they'll lay down a solid film of some polymer, some plastic, usually like some fluorocarbon. After it's laid down, they'll then run that film through a whole bunch of different chemical treatments that makes it activated for this purpose. Whereas you are taking resin beads that are already pre-activated and just grinding these up and mixing them into PVC cement, basically dissolved PVC, and then you have such a density of these particles in that PVC film that the ions are able to jump from one particle to the next and make it all the way through, while still keeping the film pretty much watertight, tight to all other compounds.
Exactly.
Yeah, it's great. So I actually looked into this ion exchange resin, and I have some experience with how this is made. And so people who have viewed my videos before, there's a video where I go through a whole process of sulfonating a bunch of different chemicals. This is sulfonated polystyrene. A little more complicated than that, but pretty much just polystyrene with some sulfate groups stacked onto it. And the sulfate groups have a very strong charge, and that makes them able to accept ions of a certain charge and reject ions of another charge. And so that makes the membrane able to work basically in one direction only. It's basically like a one-way valve or a diode to allow chemical reactions to occur in your electrolysis chamber that would normally self-neutralize. It makes the chemistry suddenly favorable for doing all sorts of cool stuff. So like, what kind of things have you already been investigating using these membranes for, besides the flow batteries that we just talked about?
Yeah, well, the mining side, like I described, so pretty much it generates acid on the positive side through the ion exchange membrane, leaches out the ore, plates it off, recycles. It's a closed loop process. But when I say we only scratch the surface and that this will change every single industry, I don't mean that exaggeratingly, and that's why I open source the patent. That's why I open source this thing, because I realized oh my God, this is going to change everything. And it's something as simple as simply the iron industry. I did a really amazing video in doing calculation. We actually found a research paper that actually used a similar process, not same as the one I did in the video, but proving that this is a real actual thing that will actually works. Again, in their case, they used very expensive commercial membranes. And keep in mind also commercial membranes are like $400 for a square foot or so. These membranes, you can produce them for less than $1 a square yard. But anyways, lots of applications in creating metals, in creating chemicals, in filtering, separation, and also into power supplies. So, for example, there's what's called a reverse osmosis fuel cell, which actually can convert saltwater and freshwater mixing together, like at a river to an ocean, into electricity, directly into electricity. And this is a real thing. There's real companies that do this. But again, the whole problem has been just the cost of the membranes, because eventually you do have to replace them. They're not, forever. And the cost to replace them is more than the electricity produced. So whenever companies try to do this, they just go bankrupt. But this is a real thing that can have huge impacts on our world, on our economy. Fuel cells, just for example, you can convert gas methanol and ethanol directly into electricity with these. Of course, you have to add a catalyst, and it's not exactly simple, but the key limiting thing, the membranes, is now unlocks all these other technologies. So in my opinion, I like to say this technology unlocks flying cars, because imagine not small, but pretty lightweight thing that can convert fuel or gasoline directly into electricity without you having a huge combustion engine with harmful emissions, and then a generator to convert it back to electricity. Well, now you're able to have that electricity power very lightweight small motors and unlocks vertical takeoff. If you unlock vertical takeoff, boom, you unlock flying cars that have the range of gasoline powered airplanes, but the flexibility of of vertical takeoff. I mean, I could go on and on and on, but it's insane. For me, the best thing that lets me understand why it's so incredible is to understand physics itself, right? Because all chemical reactions are based off on the relationship or reaction between electrons of two atoms. If you can control that directly, you control chemistry directly. You don't have any loss. It's the most efficient way to do any process. Like again, compared to an internal combustion engine, which first breaks apart the hydrocarbons into heat. That heat pushes creates pressure, which pushes a pistons, which converts into a mechanical force, which then drives the alternator. Right? There's so many inefficiencies, and fundamentally, there's actually this a thermodynamic, I forgot the name, I think it's Carvet's law or something, but there's a thermodynamic barrier on whenever you do shifts in energy potentials like that. There's a fundamental limit to how much energy you can extract. And in terms of an internal combustion engine, that efficiency is around like 30 or 40%, which is why a lot of internal combustion engines, if you look at their efficiency, they're always, 28 or, 30 something percent. Like, why is that the case? It's not that our engines are inefficient. It's just the laws of physics. And Veritasium actually has a really great video on this. But by the efficiencies of a methanol or ethanol fuel cell, for example, or even ammonia fuel cell, they can reach to 98% efficiencies directly from the fuel to electricity and no harmful waste. The only output is CO2 and water, no nitrous oxide, no harmful particulates, no carbon monoxides, clean CO2 and water.
Yeah, one of the things that I think makes a big difference with this membrane technology also, and just membrane electrolysis, is that you are able to do all this chemistry. Say, if you're making, if you have a hydrogen powered car, for example, in the current state of things, all that hydrogen is usually going to be generated by cracking petroleum stuff, by cracking fossil fuels. And so it's like, okay, you're just burning the fossil fuels in a different way. Whereas with the membrane technology, you can make generating hydrogen from solar power and things more efficient as well. Well, maybe hydrogen's an exception, because I'm not sure about that. What do you think on that?
Yes, no, you're 100% right. You can produce hydrogen, directly electrolysis, right? Water and exchange membrane to keep hydrogen and oxygen separate. As you remember that video you made a long time ago trying to build a cell, you clearly understand the, difficulty was trying to keep those gases separated. So you have to use a U channel, and that creates an efficiency, right? Because there's more of a distance. But anyways, point is, yeah, it is most definitely. There's companies already that do this. It's called e-hydrogen. You can reduce the you can use specific catalysts to reduce the voltage potential, because remember in electrolysis, the rate of reaction is based off amperage, not voltage. But my opinion actually on the whole hydrogen situation is you simply convert, because the biggest issue with hydrogen is storing it. You'll have a huge tank to store. So what if you simply convert that hydrogen into methanol?
Right.
E-methanol. And then use that to power a fuel cell. So now you have the energy storage of gasoline in a liquid form that's easy to store, right? It's liquid, but the energy density but it carries all the hydrogen. And there's real companies that do this. You can buy a unit and you put it on your rooftop, and it uses water, air to produce gasoline. Like, it's a real thing that works.
And inside these fuel cells, where you would be, so that a fuel cell, like a hydrogen fuel cell, a methanol fuel cell, takes these chemicals, passes them over one of these membranes, and converts that directly into electricity, correct? Like, it's basically, when you have a hydrogen powered car or a methanol powered car, it's really an electricity power. Like, you have electric motors in there that are running off of this chemically driven fuel cell, right? And these membranes make that a very efficient process. So when I was a kid, I may make a video about this on the main channel eventually, but when I was a kid, I always wondered about electrolysis. With water electrolysis, you have your anode and your cathode, and you put your current through there, and you get hydrogen at one of the, you get hydrogen at the cathode? I don't remember.
Negative side and oxygen at the positive side. Probably.
Actually, yes, and the positive and negative is different depending on if you're talking electricity or chemistry,
Yeah,
which is so annoying.
A lot of chemists are going to watch this and hate me for saying negative, positive. I'm sorry, but
Yeah, it's totally
depending if you're
confusing because
discharging or
electrician-
charging,
yeah.
it flips.
Yeah. Anyway, so at one side is hydrogen comes off of one of the electrodes and oxygen off of the other, and I always was like, man, how are the water molecules splitting in the middle of this tank and flying to the other sides? And it wasn't until just a couple years ago that I realized that you actually are not doing a simple splitting of H2O. You're actually at the one electrode, you're generating OH ions, and at the other, you're generating H plus ions through two totally different chemical reactions. And then so one of these generates oxygen, one generates gaseous hydrogen, and then the remainder of these byproducts comes together in the center of the tank and neutralizes. And so the net effect is that it's H2O equals one oxygen, two hydrogen, but really it's two very much more complicated chemical reactions that neutralize each other in the middle of the tank. And what this membrane could do, if you have a membrane divided tank, is it could still generate hydrogen and oxygen, but the two side reactions that are occurring at each electrode, one generating OH, which is a very alkaline molecule, and then the other generating free hydrogens, which are very acidic, you end up getting a pH difference across the membrane, where on the one side you're creating alkaline molecules, on the other side you're creating acidic, and those are very useful for all sorts of other chemistry. And so, like, that's one of the things that these membranes could be good for if you want to generate like sodium hydroxide from table salt. Sulfuric acid from table salt. And you can do all of this with any electricity source. And that I think is really cool. You had a video, you already referenced it a little bit, about generating iron using one of these cells. And this is a way where you could refine iron with any electricity source. Solar power. You no longer need to use the coal refining process where you're mixing your oxides and blowing it off with carbon monoxide to get your raw iron. You can just do this with clean solar energy or nuclear or whatever. The topic I talked about on that video, it just scratched the surface. Like, here's another example. Because this electrolysis is at room temperature, right? It doesn't really have a temperature it has to heat up to. You can turn on and off this unit like that. So that unlocks access to renewable energy. That's the issue with a lot of, green technologies or green industries that want to transition to renewable energy. Like, for example, with arc electrolysis to produce steel. Well, it needs to be a 24/7 operation. You can't just shut down the whole plant and wait until the next day. You'd lose your temperature, and if your efficiency would go down the drain.
Exactly.
So with the electrolysis cell, nighttime comes, your solar stops working, no big deal. Starts back up in the morning, even without batteries backup. That's awesome. Yeah.
At most, you'll probably leave a little bit of a voltage potential to not have the negative side, let's say, redissolve or whatever, because it's as it transfers through, the iron actually reduces down. So there's a little bit, but I mean, worst case situation, if it turns off completely, you're not losing much at all.
Right.
Fundamentally unlocking that capability of just turning an entire industry on or off is huge. And again, I hope also people won't come with the misconception that, this is a very slow process, it's a very energy intensive process, whatever. No, remember, this is the most direct way of doing chemistry, and melting or producing iron metal is a chemistry process. You have to reduce down the iron oxide to iron metal by adding coal to have that react with the oxygen, and to produce 1 ton of steel will cost about, I think in that video I have sources that show it's $550. That's the energy input. That's the chemicals used. That's the whole 9 yards, right? That's not producing. Also, that's not hammering down and producing ion beam. No. That's just reducing down the steel. But our process, using ion exchange electrolysis, you can produce iron for less than $200 a ton, and that's pure iron. That's not dirty iron. That's not X country steel, as many of us know.
It's not pig iron that needs further processing to get all that iron out of it to turn it into proper steel. That's awesome. I mean, can you talk a little bit about the mining setups that you have developed and some of the results that you've had?
Yeah, so I have a presentation that actually shows the rare earth elements and all the 9 yards you can actually see. But currently I have two different setups. It's called a continuous mining unit and a continuous refining unit. The continuous mining unit, like I said earlier, it uses saltwater and electricity, primarily hydrochloric acid and a little bit of salt water to produce the sodium chlorate, and that is capable of dissolving iridium, rhodium, platinum, gold, etc. In fact, this is how people already basically use. If you ever look into this, you can look into bleach extraction of catalytic converters. This is how a lot of people do it in their backyard. They'll add bleach and hydrochloric acid, and that produces similar chemicals. In fact, weaker, but similar chemicals to what
Is that aqua reagent? Is aqua
No.
reagent hydrochloric acid and sulfuric, or is that
nitric? Aqua regia is nitric acid, and actually, it's a way weaker. So, aqua regia cannot touch platinum group metals. It cannot dissolve rhodium. It cannot dissolve. That's why this technology is so amazing, or why using salt water is so amazing, because you're actually capable of dissolving one of the strongest oxidizing. It's called the ORP level, oxidizing redox potential level. That's capable of dissolving these very, very, very noble platinum group metals. So I call this process sol regia. So aqua regia, that's a new term I want to actually start pushing out in the industry for people to use, because that way it differentiates from aqua regia. So again, aqua regia uses hydrochloric acid and nitric acid. This uses hydrochloric acid and sodium chlorate. And remember, the most important thing is the hydrochloric acid. The nitric acid or the sodium chlorate, all that is an oxidizer. So you could think of it like a catalyst. It doesn't actually dissolve or react with the metal. It just provides oxygen in order to in order to have the hydrochloric acid do its work. So
sure pushes it forward, just like a piranha solution, hydrogen peroxide and whatever exactly. That is. Yeah, hydrochloric.
So that's the mining cell, and what's key about that is you're able to extract as low as $20 or $50 a whole ton of minerals. So you have this huge ton of rock. You dissolve all the heavy metals in just concentrate powder. Have this clean rock that's safe for agriculture. And now with the concentrate powder, you have a mix of rare earth elements, precious metals, gallium, all the heavy metals, right? But what's key about this is it's in a concentrate form, right? You're not, working from a whole ton that only has a couple ounces. No, you're working with the couple ounces. So that actually can be refined traditionally through various refining techniques. But what we've developed is called the continuous refining unit. It uses the same principle. Positive side generates acids, negative side reduces them, closed loop process, right, flows through. But what's critical is you change the acids. So, for example, if you switch over to acetic and nitric acid, you can now separate almost all the base metals and leave behind the precious metals in a single step. And this is really huge in the refining industry because for example, a lot of people, they have dory bars or whatever that can only have that only has like 5 or 10% gold, or even less, or maybe in the less than 1% gold, and refiners simply won't take that. It can have a lot of mixed elements. It can have iron, it can have lead, it can have arsenic, it can have all these other base metals that refiners, they have in their list, like, hey, we're not going to take this because it's such a pain to try to traditionally separate it all. Like, for example, to dissolve 1 ton of iron, you need 3.5 tons of nitric acid. Now, for those that haven't ever purchased nitric acid, look it up. It's incredibly expensive. Like a 1 gallon jug is like $60 or $100. It's incredibly expensive, and you need 3.5 tons of this. Okay, incredibly expensive. But our process is able to do it for less than $200 a whole ton in electricity.
So how is it able to do it for that inexpensive? Like is it because you're generating the acids in the cell itself?
Yes, because think about it. You to produce nitric acid or traditional process, firstly, they don't use electrolysis, they use a different process. So they have to do a multi-step process through a traditional method to produce the nitric acid. And then they have to put it in a container, ship it to you, you get it. And then also that's just the cost of nitric acid. That doesn't include the cost of neutralizing it, disposing it, so forth, right? But if you have a continuous process where you continuously regenerate the acid as you reduce the metal, you solve that whole problem. And you could actually use the electrolysis cells to make fresh nitric acid from like sodium nitrate or ammonium nitrate, basically fertilizer. So tons of potential.
So it's basically like the battery that I was discussing earlier. So you have your you take your acids, your reducing agents, your oxidizing agents, you use it to dissolve the metal out of this raw ore. And you can kind of guide that process depending on what metals you want to dissolve preferentially at the time. Feed that into your electrolysis system, or even maybe that's part of the electrolysis system in this closed loop. It goes into the electrolysis cell. The metal is extracted, and in the metal extraction process, because at the anode and the cathode, you have these two different reactions going. On the one, it's depositing the metal. On the other, it's becoming acidic again. So on the other side of the cell, you're regenerating the solution that originally dissolved the metal. So that can go back into your ore refining process and dissolve more metal out to come back in. Yeah, I mean, that's awesome. And so like, you're just
so simple.
Yeah.
How did nobody think of this before? It's so simple. Like, but again, it's all about taking a step back and, fundamentally from the membranes. When I first released the video, people were like, oh, how did you come up with the membranes? How did you come up with the membranes? And everyone kept bringing up a post-sulfonizing, functionalizing using sulfates or whatever groups to, try to activate the membranes afterwards. Not a single person came up with the idea of using pre-functionalized resin. Not a single person. It's all about taking a step back, reviewing the overall picture of things, and seeing how can you integrate all of this together. That's something that a lot of people just struggle with. I don't know why, but for me, I'm luckily talented.
Why do you think? I mean, even at Nafion is the commercial membrane that most people know about, and why do you think that this would not have been done yet with that membrane, even considering the cost?
Why did Nafion not use a similar process? You're asking?
Yeah, why? I mean, like, why would this process, being as efficient as it is, not still be worthwhile even with a membrane that expensive? Or is it just like, I mean, the barrier of entry is too high?
I'm sorry, I don't quite understand that question. You're asking why does... I don't understand that.
Like the mining technology of using like
Why don't they use Nafion? Oh,
right.
Okay.
Why didn't this pre-exist, even considering the high price?
Because, like I said, a couple reasons. First reason is the high price. If the price to replace the membranes is more expensive than the end product, it's not worth it. Second problem is Nafion is very. I mean, for me, Nafion is like the I kind of trained myself to use it like the word Voldemort, or the name to not be spoken. So commercial ion exchange membranes.
Generic.
Yes.
Non-company specific membranes. Okay.
Exactly. The generic non-company specific membranes, they typically are very prone to what's called fouling. So fouling is when, especially in mining conditions, like not a single person would ever think of using an ion exchange membrane for mining. You're talking about some of the harshest acidic conditions, some of the dirtiest mixed metals. You don't even know what the hell is dissolved in there, right? It's so problematic, such a headache. And chemists like control. They like everything to be pure. They like everything to be, consistent. And for them to try to use this really sensitive membrane on something that's very, very dirty, it's just they will never in their life connect those. So that's one of the biggest reasons, because at the end of the day, you just put that you put probably these other commercial membranes in one of my refining cells, and it'll just get destroyed. So what they typically do is they'll actually specialize on making a membrane for a very specific application. None of them try to create a generalized membrane, right? Because again, why would they? They spend tens, hundreds of millions of dollars just to develop one membrane. Why would they use, if they're going to do that, they're going to optimize it to increase to the extra 3% digit points of efficiency in order to make, the millions of dollars worthwhile. But if you do that, right, it's if you make a tool very specific for one job, it pretty much loses function in almost many other applications. And, they typically don't want to, like, for example, they'll make membranes that is very specific to very specific ions that pass through. And again, I can do that with my process too, and that's something we want to research into. But none of them ever think of trying to make a generic, X company membrane. If you actually look into their product sheet, they have like literally thousands of different membrane types specifically because of this.
Okay, I mean that makes sense to me. I mean, you see that in different industries. Being someone who's been a YouTuber for pushing 20 years now. I always wanted a high-speed camera, and at the time, high-speed cameras were only ever made by like Phantom, and it's like $1 million camera to buy it because they're not made to film cool science projects on for the internet. But suddenly, like, people realize, okay, regular people also want these cameras too, and then you can make a generic model that doesn't quite do the specialty stuff as well, but it's $5,000 instead of $1 million. And so so it's just the normal process of industry of having that niche company that makes a lot of money on technical fields, and then someone else wants to come along and generalize it later on. Okay, yeah, that makes sense. I wonder if I can get you a pic. I'm kind of bummed I wasn't able to do this live stream from my phone. I want to see if I can get you. Can you see my desk? I kind of want to do a quick demonstration for people just to see. It's a little late in the stream now, but I just want to show like how easy it is to make one of these membranes. Basically, the way that I made my first one, which is still yet untested, but I'll be testing it shortly, probably today. Take some of these resin ion exchange beads. And then there's anion or cation, correct?
Correct.
Of these beads. And so depending on what you're doing, most of the stuff that you would use would be the more common cation resin. Would that be what you use in your mining cells as well?
All right, cation. I mean, there are certain applications we want to use anion for, like, for example, to separate, let's say we build up too much acid, we actually want to separate it, so we'll actually use anion. But cation is typically, for most cases, a lot less sensitive, a lot easier to work with, a lot just more because it would, again, if you split sodium chloride, you'll get sodium hydroxide and chlorine, right? The sodium is the cation, the chlorine is the anion. So the sodium is what would pass through cation exchange membrane.
Gotcha. Okay, so so then you recommend using like one of these high-speed grinders to grind this powder down. Actually, you recommend a ball mill first and then a grinder to break it up, correct?
Yeah. So it depends on the application. So that specifically what you just mentioned is actually for anion, because anion here, let me actually show you some anion.
Let's deal with, okay, sure.
This is some anion. So there's actually what I ball milled. And as you see, it is almost like, you can actually squish it together. There you go. It's like it just squished into like it's almost like a putty. Honestly, like a putty more than anything. And because that's really hard to work with, it's a really interesting smell also. But because of that, like with the cation, you could literally just blend it directly, and it almost immediately turns into powder. Of course, in your case, like you're probably going to mention, is be very careful about the water concentration, or you don't want it too wet because otherwise it'll stick to the casing. But I've spent literally probably almost a year and a half experimenting with different blenders, different types, and that high-speed blender is the one that works out.
Yeah, there were a lot of generic ones on Amazon, eBay, $40 to $80 more or less. But so yeah, I blended some of these resin cation exchange beads down, which are sold for water softeners, and they turn into this nice powder. And you just lay some of this down, and you've been mixing by volume, correct?
Yeah, I just mixed by eye.
By eye. Okay, so I would recommend trying to standardize that by weight, just for easy repeatability. But so like 50-50 powder by volume to PVC cement?
Exactly, so 50-50, just eyeball it. You don't have to do anything crazy.
50-50 OD PVC cement mixed with this powdered ion exchange resin. This is not the vessel to mix this stuff on easily, but it does mix into the PVC cement. I use
disposable cups because the PVC cement, like it dries up, and when it dries up, it sticks to basically everything. So just use a disposable cup. That way you don't have to worry about trying to clean it off afterwards.
Yeah, actually, this is a silicone mold, and I found that it actually swells from the solvent of the PVC cement, but it dries out and it peels off clean. Nice. So yeah, this has been easy. And then the membrane, as I made, excuse me, the membranes that I made earlier, are pretty fragile if they're not reinforced. This is just some that I made earlier. And then this one is fiberglass reinforced. I don't know if you've used this kind of fiberglass, this like woven.
No, I'm too broke to do that. I use the frayed one. I don't know if you know that one. It's not the woven one. It's that's what I use.
the kind that you blow. It like kind
Yeah.
of blow into an empty cavity or whatever, or blow onto like a boat hull or something. This woven
Yeah.
stuff though, it's interesting. I kind of liked working with this because I didn't have to like measure my coats. Because if I take a piece of this, and where's the edge I cut on already?
It surprisingly is really like permeable into fiberglass. Even like that one that I was describing, like the the non-woven sheets.
Yeah.
Like if you just apply it and you try to peel it off when it's wet, it just all like falls apart. It's like I don't know why, but it's really soluble in fiberglass.
Okay. Yeah. I mean, it soaked into this really well. The reason why I liked, I mean, I just had this woven stuff on hand. I didn't go out and buy it specifically for this, but the reason why I liked the woven stuff is that it like kind of gives you it gives you a consistent depth. So like instead of spraying it on, since I just pooled it on there, and now I can just like brush it into the fiberglass mesh to the depth of the mesh. And so like,
That's
like
a really good, nice job. Wow, that's
isn't that
unique.
cool?
Yeah.
So like, that's like a really easy way. Like, here we go, membrane done.
Yeah.
Like let that dry for like, I don't know, an hour.
Yeah, you don't want to let it dry all the way. That is one thing that even the powder after you pulverize it, I would keep it in a sealed container. You do want it to still keep a little bit water.
Okay.
I'll make an updated video about all that because definitely noticed people having. I didn't specify that enough in the first video.
Okay. Yeah. But anyway, there you go. An ion exchange membrane, a cation exchange membrane that's ready for, use in flow batteries, use in electrolysis projects. Just crazy how easy that is. Yeah, just awesome. I mean, simple stuff that you can buy. I don't know if you can buy the resin beads. Probably you could buy them at like a water softener, installation place, some kind of local company or whatever.
Water softeners. You can use beads also.
Oh, like old beads or whatever.
Yeah, that works.
Oh,
also.
cool. Yeah. So, I mean, geez, you could almost get all this stuff in person. The resin beads I bought on the internet, but I mean, yeah, it takes nothing. That's awesome as far as accessibility goes. I just made one of these in 5 minutes, less than 5 minutes. And I'm going to put it out. Give me a second. I'm going to put it outside now because it's stinking up the place. Yeah, Robert. I mean, what you've come up with here is really awesome. I was wondering. You just mentioned that you don't want to let the ion exchange resin dry out, and that
Yes.
Every time you buy this stuff, the warnings about not letting it dry out are plastered on all the information about the beads. And I was wondering, are you sure you can't let it dry out? Like if you let it dry before you put it in the membrane?
It reduces the conductivity quite a bit because remember this diagram very well. And there's a much better study that draws this way better than I did. But you can actually think of this black as PVC, right? And it actually forms around it. For example, if you try to mix those beads up with the PVC directly, you'll notice the PVC doesn't bind to it. Like the primary reason, like a lot of people ask is, oh, instead of grinding together, why not just mix it with PVC resin? Well, the reason why is because it doesn't form an actual bond with the PVC. It actually has a bit of a gap, and by grinding it down, you're able to encapsulate those particles completely by PVC, and that creates a rigid structure. But why that's very important is because if you completely dry that out, then this is not going to have water. This is not going to allow ions to easily pass through. You could let it soak in and take some time and apply a higher voltage to kind of force ions to go through. But definitely I noticed the conductivity decreases by a bit.
Okay, so you have experimented with that. I gotcha. Yeah, I mean, I was just thinking for consistency's sake, it might be easier, but I mean, I was trying to think of how these membranes worked practically. And so you're able to do this, obviously, like just mixing powder by eye 50/50 shows you that like this doesn't take a lot of precision to make a functional membrane this way.
Yes. They work so great that optimize them because they work. My focus has always been the mining technology, not on trying to optimize the membranes by an extra couple percent, which definitely it needs to be. And we already have ideas, and I have a Discord server where people already came up with some great ideas on how to increase the conductivity even better. Like for example, soaking them in salt water or other stuff or other chemicals to actually put in those ions in the first place. And point is, there's a lot of more improvements that can be done on this, but I mean, as a start, they already work, and as a start, it's already way better than anything else they can do.
Right. And so so what I was thinking is like, suppose this membrane isn't optimized because I didn't grind my powder finely enough. What I'm thinking is that all that would do is cause the resistance to be a little bit higher, right? With the membrane. And so it would still work just as not the resistance necessarily, but like the
separation.
The optimal pathways through this membrane would be fewer. And so like you would just not get as much, you wouldn't be able to, you wouldn't have as much surface area. You wouldn't be able to drive as much current through it without increasing the voltage to sub or higher than optimal levels. But like if you just kept the voltage lower, it would still be optimally efficient. I don't think you'd lose any efficiency. You just lose like how much current you're able to drive through it.
True. That is the case. Because remember with electrolysis, the reactions is based off currents, not voltage. So if you run a reaction, let's say at 1 volt and 1 amp, or 10 volts in 1 amp, you have the same amount of reaction producing. The increased voltage means increased wattage, and it ends up being heat or whatever that is wasted.
And increased side reactions, right? Or like you would start being able to react with your anode and cathode or something a little bit more at those higher voltages.
In some cases, yes, higher voltages can result in different. Sometimes you want a higher voltage because certain reactions need a certain voltage, right? Obviously, you can't be running everything at 0.2 volts, right? You can split water at 0.2 volts. But yeah, running at higher voltages could also create side reactions.
Okay. Anyway, I was just trying to explore like maybe what the downsides are to having to like if you put a ton of effort into milling the powder as fine as possible and all that versus not milling it that fine. I wondered about if that really affects efficiency that much or not.
I would say it's more for like DIY, not really for commercial scale. Yes, because trying to blend, right? You're not going to be able. You'll notice like when you use that blender, you'll find some whole intact beads. Not every single thing gets turned into a powder, but with ball milling you have a lot better consistency. I actually bought like I think it's like 30 pounds of marbles in order to create a really big,
it's crazy how much it takes to fit in a ball mill. Yeah.
Well, but I mean realistically it's not that expensive. In a 5-gallon bucket, and boom, I have a pretty significant production scale where I can kind of mass produce these membranes, because you don't need that much to create a large surface area, as you see yourself. I mean, I buy mine in the big bags. I mean, I'm just surprised you bought it in the small bags. But I buy like the big, I think it's the half cubic yard ones, and they go for like $40. They're not that expensive.
Yeah, well, I mean, I figured this would be enough for me to make a lifetime of membranes for my use. But yeah, I mean, it's cool stuff.
This is my collection.
Nice. Okay, so you to keep it hydrated, you fill the bottom with water. Okay.
Exactly. Yeah, I think I mentioned this to you or not, but yeah, this is what I mean. I'll make an updated video explaining. Clear container, you just fill up the bottom with water, and it'll keep everything humid. You actually see water droplets at the top, and that just keeps this. Like if you scoop from the surface area, you actually even see the layer differential. If you scoop from this, it ends up being like the perfect humidity you need.
Good deal. Yeah, the bag that I had was laying on its side, and so I think I got some of the more water soaked stuff from the bottom of the bag when I tried to mill it, and you can see it. Yeah, it sticks to the lid on the inside of the container and all that. But
just don't let it dry out too much. Like I said, don't let it dry out too much. And I recommend, like you saw with the anion, I just keep them in little containers, and after they pulverize, they're typically fine. But definitely it needs to be optimized. Definitely, experiments need to be done to find the optimal, ratio of humidity and so on and so forth and so on and so forth. And that's part of why it's open source, right? To have a community actually work on this together and, combine our resources, because it's hard for me to do everything myself.
Yeah, I mean, it's just so cool that it works with so little optimization. That is, I mean, that's beautiful. You're going to want optimization for commercial stuff, but it's just the perfect perfect thing for experimentation on a small scale too. Yeah, I mean, it makes me think too. I've done a lot of experiments that require ultra high density pigment packing and paints and things like that. And so for that, you want multiple particle sizes. So not just the finest, but you want to fill in the gaps of larger particles with smaller ones with smaller ones. So like you could probably make these even way more conductive than they are now, but doesn't seem like it's necessary in the meantime.
Exactly. This is something that for me, I guess, is, I don't know if this is a curse or a blessing, but for me, if I follow a chemistry instruction and I follow it step by step, I'll mess up. I'll completely fail every single time. Even cooking also, especially cooking. I'll try to follow a cooking recipe, and I completely fail. And every single time I have to completely redesign my own procedure, my own steps on how to, do this. And ends up being a foolproof method of how to do it and better than the original recipe. I don't know if that's a curse or a blessing, but what I have to experience.
Hey, well, this is a really cool project. You want to tell people more about like what you're working on now as far as this project goes and where you'd like to take this?
Yeah, I'm right now actually doing this. This is a little test electrolysis cell. I mean, this is way smaller than what I actually build. You can see, again, I'm trying to do so many things at once. I'm trying to launch the website, trying to do this, so people can help support the research, and because this analytical equipment right here, it's a Rigaku NEX DE, which, by the way, if you ever want any analysis done on elemental analysis, I don't know if you ever want to, but no, they have a XRF machine, a $67,000 piece of analytical equipment. Fixing up a wavelength dispersive XRF. For those that don't know, this is a beast of a machine. It outputs 4 kilowatts of X-rays.
Gee whiz. And this is all for analyzing the outcomes of your mining processes and things.
Exactly, because a lot of PGM, well, not a lot, but pretty much almost always PGMs are in the low parts per million or parts per billion. So if you're trying to leach that out and you want to do what's called a mass balance, pretty much you analyze how much is an original sample and how much you extracted, right? See exactly where everything is going. You really need a much more sensitive equipment than something like this. And even then, that machine isn't enough. Like I applied for some grant applications, and actually, fingers crossed, tomorrow we should know the results of the last one that I applied for and took 3 months writing for. But that one.
So you're building out a lab. You're applying for grants for optimizing your mining process, or
correct, optimizing the mining process, scaling up to a tonnage per day system, and then also to have a full research and development facility where we can have analytical equipment that will give us access to parts per trillion detection limits and other analytical equipment, so we can see what the composition and what's going on in chemistry fundamentally at the fundamental level, and also to be able to mass produce these electrolysis units. And that's a really big thing, because
not just the membrane, but you want to mass produce a system targeted on mining right now.
Well, that's what's interesting. So yeah, right now we'll target on mining, because obviously that's what the grant is for. But once we have that capability, that electrolysis cell can be reused for chemical production, reused for redox flow batteries, reused for this, reused for that. Like, the fundamental electrolysis cell has a million different applications, and transitioning from one to the other becomes way incredibly easily. And the whole grant application we wrote up for is for $10 million, which is incredibly cheap. I mean, I'm looking at other grant applications and awardees, people spend 80-90 million dollars just to research and prove a technology, whether it works. Like, we're beyond that stage. We're what's called a TRL level, technology readiness level of a 5, where we actually have proven material produced, proven, third-party analysis also showing that we've extracted rhodium. I mean, fundamentally, it works. There's no question of whether or not it works. It's just a question of scaling up, and that's something I can't really do. Because, again, even simply to scale up to a 1 ton per day system, I'll need heavy equipment to unload the rocks, right? Heavy equipment to crush it down into a powder, to load it in a continuous vacuum filtration drum, which we have a GoFundMe for. That's just from China. That's a $25,000 piece of equipment. I mean, I go on and on and on, but being able to process tons per day, that's not something you really do in your backyard. It requires industrial capacity, and it's rough. I mean, because a lot of people say, "Oh, just start processing e-waste, just start processing ore, and make your own money." Like, you kind of don't understand what you're talking about. And the most important thing is to first do a business analysis, see what is the mass balance of ore, what is the mass balance of e-waste, and you'll find out, especially with ore, like it'll probably be a thousand. Normally, gold ore is at 1,000 or 2,000 per ton in value. And now we do have access to gold ore, and in fact, I'm even sitting on some 1,000 pounds worth that's valued at $5,000 a ton. But still, think about it: $5,000 a ton. Well, you have to process at least a ton a day in order to make it worthwhile. Otherwise, I mean, processing 10 pounds a day, you're making below minimum wage. I might as well go, to work at McDonald's or
Sure,
go back to
sure.
my pig farming. But yeah.
Yeah, it's awesome. I like people like you that are really have dived into, like, you're put, I'll take all these concepts and I'll investigate them at the surface level. I'll get, this deep, and then I'll move on to the next one. And, I'm just like investigating things at surface level, in order to get other people to really dive in like you have into these niche areas that actually can make a big difference. And so, yeah, I love what you're doing, and
I hope people can recognize that, because I can't stress it enough. I get really frustrated with a lot of climate activists, people that, say, well, we need changing this, right? We need to, what I like to say is they like to talk about talking and how to talk about talking. Here I am doing the hard work. Here I am. Like last year, we spent probably almost $250,000 just last year. We had a donor that had significantly helped us, but almost half of that was from my own money. That's a lot, and I didn't get a single dollar back. Like, I basically, I mean, I don't have bills because I own my property.
What did that go into doing?
The facility itself, I mean, we have an entire facility that I built. All this I built myself. The only thing I built, or the only I paid people to build, was the concrete and the roof and framing, because obviously you need a crew of people to do that. But everything else, the mezzanine, the cabinets, the interior walls, the exterior walls, the insulation. I have a spray foam rig. I have the whole 9 yards. I did all that myself. Of course, that's not cheap. That all adds up. Buying a CNC machine, the analytical equipment. This one, even with this one, like, for example, I think we spent about $2,500 for this. I mean, brand new, they're almost like $300,000. So, but just the software for them, I had to pay $5,000. Right, the calibration, I have to spend another, $5,000 or $10,000. It adds up. It all adds up. Chemicals, materials like the PVC sheets to make the clear, these clear PVC sheets. I mean, just one of these sheets is like $300 or $500 with shipping. I spent thousands of dollars on some ceramic filter plates I did to experiment, try to build my own continuous vacuum filtration system. I spent almost $1,500 on that. Just chemicals, for example. Right now, one of the things I also want to try to do with this Electrolysis.
Do you have one of your Semtech units available to look at?
Yeah, I'll take you outside. So like another thing, for example, is I'm trying to build or trying to test a way to separate lithium from salt water. Pretty much to selectively also recover lithium from, let's say, batteries and stuff. So it's lithium selective membranes. And just to experiment that process, just to experiment whether or not my theory works, I had to spend like $500 just in chemicals just to see if it works. So it adds up.
Yeah, one of the things that I've been looking into recently is geopolymers.
Yes.
And one of the things that if you are doing saltwater electrolysis to extract minerals, one of the first things to precipitate out is magnesium hydroxide, which is one of the precursors for many geopolymers, and this could be very useful for that as well. So explain what we're looking at here.
Yeah, so this is the continuous mining unit. Pretty simple. We have the negative electrode. I have a titanium electrode. I have a titanium bolt at the bottom. I don't know if you can see what I'm seeing, but am I showing? No, I'm not. There we go.
There we go. Yep.
So we have titanium bolt at the bottom. It holds a polarity charge because as a polarity charge, because as the metal plates off, obviously it'll fall down. You don't want it to redissolve. So, it just keeps the voltage potential here at the bottom. But yeah, up here, positive side regenerates the acid, flows out through the leaching tank. Obviously, I don't have one right now. And then it pumps. This pump actually pumps it solution through back to the negative side, plates off the metals, and it has a bypass chamber right here. Actually, brings it back to the positive side and repeats the cycle. And here's some electrodes I built. I mean, just just the electrodes themselves are a very unique design that I'm gonna make a video about soon. But like, look at this thing. I
Yeah.
had to develop a whole manufacturing process to coat the top to, like, how do you solder? Like, think about it. How are you going to solder a wire to graphite?
Right. Right.
I had to
Yeah.
develop a entire unique process of doing that, testing different alloys and stuff. When I come out of it, you're gonna be like, "Holy shit, that's so." Sorry for my language, but oh my god, how is that? That's so obvious. How did nobody come up with it? But I had to experiment. I had to spend my time, spend my money. And I'm open sourcing it all. So it's. I mean, it's and then the coatings to prevent them from getting. I mean, that's pretty simple. I just diluted some PVC cement with acetone. This is another electrolysis cell. Here, let me show you all the different electrolysis cells I built. Here's another one. Here's another one.
Hmm.
I have more right here. Here's another one.
So take me back to the original Semtech unit, or the Semtech unit you got there. So this
Yeah.
is so this is where this is just a part of your closed loop system where you would have a big like dissolving tank for ore attached somewhere down the line. It would pump into
This tank right now, I cleaned it out already, but yeah, I just have a barrel in the bottom. I have filters. There's actually some of the filter that I keep in the bottom. This is my chemical waste that I actually want to develop another system that can actually separate. It can run mining waste, separate separate all the dissolved metals, regenerate the acids, and then run that through an ion exchange resin column that can also be regenerated with electrolysis. But pretty much you put in toxic mining waste in and get out clean actually it's called ultra high pure water. It's the cleanest water you could ever produce for mining waste incredibly cheaply. I've done a test where I've dissolved, or mine company actually sent me some solution. I ran it through my electrolysis system, and within 10 to 20 minutes, I was able to reduce all the metals. Now, keep in mind, they put this solution through like 5 different filtration methods to try to separate it. As clear water. I was shocked myself. But within 10 to 20 minutes, reduced all the metals out, and now you can simply filter those metals, and boom, you have clean water. And the cost for that was less than $5 for a whole ton of mining waste. Like, there's no way to beat that with using chemicals trying to reduce it all down. Or you want me to go back? Oh, sorry.
No, that's fine. No, that's good. Yeah. Hey, Robert, I think that this was a great. I mean, is there anything else you want to say before we sign off? Did you say you have a website that's also the same as your YouTube channel, ROWOW, ROWOW?
Yeah, ROWOW.
.com?
Yeah, no, .net, .net, .net.
ROWOW.net. Okay.
Yeah, hopefully, again, please, this all costs money, just the CNC machine, I had to, I had to buy this, I had to fix it up, I had to, put a lot of time into this whole facility, as you see, this is not, cheap to produce, and it all costs money, it all costs time, and, my whole thing is this technology has far more impact than I can ever, control or maintain. And if I can simply have my philosophy is similar to rep wrap and 3D printing. I'm not sure if you're familiar with that. Are you, or no?
I think that you mentioned it to me before, where they take 3D printers to print 3D printers.
Yes. Well, exactly. But his whole thing is he open sourced 3D printing. Literally every single 3D printing company you see is thanks to that man open sourcing that. He's a huge inspiration to me, a huge life model. And what's interesting is if you look back at all the 3D printers companies that came and went, he's like basically the only one around since all this time. Right, RepRap, they're still the innovators in 3D printing. They're still the leading company in 3D printing, yet they didn't go bankrupt. They open sourced this whole technology. Yeah, all these other companies that came and went, they went bankrupt. Thanks to that, I have my career, right? Because of that, I got into 3D printing. I learned CAD. I was able to get a job in construction, doing blueprints and stuff. And thanks to that man. And that allowed me to get a career in, drafting. That allowed me to purchase this property, get it, like, thanks to him. The amount of change that man did, I don't think people realize. And this membrane technology is going to have that much of an impact. And I'm not saying this thanks to me, but I just want to live in a world where we can use fuel cells. I want to live in a world where we can use redox flow batteries. I want to live in a world where we don't have to have mining pollution. That's one of the biggest inspirations why I open sourced it, because the very first year I didn't have this analytical equipment, and I tried to find. The first unit I built that was able to process 70 pounds of ore. That took me approximately 2 to 3 months from start nothing to actual unit processing ore. Produce the powder. I'm like, all right, what do I do with this powder? I did chemical tests, shows there's precious metals, but I don't, how do I separate them? How do I, like, even if I do some chemical procedure to separate them, how do I know what I have is what I have? Right? How do I know if it's this platinum group metal or this platinum group metal? People think it's easier than it sounds. No, it's like a 20-step procedure for each element. Plus, the chemicals themselves cost more than the precious metals, and it's just incredibly expensive and so forth. So we tried to find a refiner, tried to find an analytical lab. There is none. There's absolutely none. We spent a whole year just, like how I.
So you built out this lab to answer the analytical needs as you're doing this stuff. You've already open source patented the membrane technology, right?
Yep.
And then, so what you're looking for now is what commercial partners to help you R&D the complete mining setup.
Yep.
So you have basically your electrolysis cells pretty well designed. You also need to build out the whole closed loop to be able to process these things, and what you're looking for industrial partners and funding through
angel
your GoFundMe
investors, grants, anything, because, like, for example, like I showed you, I have probably 20 or 30 electrolysis cells built. That's just for the electrolysis system. But, like, for example, chlorine gases get generated. I have to recapture that. I have to re-inject that into the system. That needs its own system, right? Sodium ion buildup. What happens when, let's say there's salt in the ore, in a continuous process, as it goes on and on and on, you're going to build up your sodium, you're going to build up your calcium, you're going to build up, your other metals, but that doesn't really plate off. So, especially the sodium. So how do you deal with that? So I have to build another electrolysis unit, a standalone cell. The sulfuric buildup, right? Let's say you're processing sulfide ore. Well, you're going to produce either sulfuric acid or even toxic hydrogen sulfide gas. How do you integrate all that and have these all other components? I'm going to have to build another 20 different prototypes of each one of those accessory systems in order to have the system fully continuous, and that costs money, that costs time. And I have a huge list of companies that are willing to buy a ready, like, for example, a shipping container or a trailer sized unit that can process a couple tons a day. I have a huge list of companies ready to buy that. Nobody's want to put in the risk and time and money required to build that first prototype, because it's not going to work the first time. It's going to need optimizations. It's going to need improvements. It's going to need very expensive analytical equipment, and that costs money. I tried buying a Chinese XRF unit. I tried looking to building my own XRF unit, and just like, for example, trying to build your own, the calibration material, right, to calibrate the spectrum costs more than trying to just buy one. It's right, like, how, think about it. You build a unit, okay, and then how do you calibrate the spectrum? Okay, now you have to get calibration samples. Oh, how much does that cost? Oh, wow, that's expensive. The Chinese one, I tried cheaping out and bought. We got scammed $18,000 on a Chinese XRF unit. There's some things you just can't cheap out. There's some things you can't DIY. I had people sell, like, for example, my roadway, it's a sand road. I had people say, this one guy say, oh, sell your analytical equipment to buy a road paver, in order to pave your road. I'm like, people always want to try to, like, tell me what to do, or, tell me things, instead of, like, the best thing you can help out ignoring money is spread the word. And that's why I'm so thankful that, you're helping with this podcast, like, just spreading the word, having other people copy the system, having other people show that this technology works, and getting it more mainstream, getting it more popularized. That is the most important thing we can do for this technology. So some company, even if it's not me, please let it be me, because I have so many other ideas. We only scratch the surface. But if somebody else wants to do it and help save the world, please do it. Somebody. If not, then I'm here. I'm ready.
All right. Well, hey, thank you so much for your time, Robert. I'll put links to your YouTube channel, which you just posted like an hour-long presentation on like your whole system, which was really helpful for me to go through. You have lots of past videos. I really liked your one on iron refining being possible with solar power. Lots of stuff for people to check out on the YouTube channel to see how you got to where you are. And yeah, thanks for open sourcing the membrane design, making it. Making videos on your channel to talk about this and kind of show all the potential and the ease of use. And yeah, I hope you go far with it and you find someone to back the whole project. So, all right, man. Hey, I appreciate your time. I will
Yes.
I will certainly talk to you again.
Yes, sir. Thank you so much. I really look up to you. And again, thank you so much. Have a great day.
Hey, thanks, Robert. All right, bye.